Good morning, Fancy Meat Computers! How's everybody doing? I hope that today has not been a bad day so far. Hope your day has been free of rabid wolverines. How's everybody today? Hopefully you're doing okay. So I posted some stuff to Avni, which may be of interest to people. It's kind of like if you want to might want to give those lectures a watch if you've got time. Yeah, I've done like 5 offerings of 1MD3 online now, like 4 or 5 of them. So you can choose the summer 2021, the winter 2021 edition. Whatever you want, really. So if you are one of those type of people who just does not have enough to do and wants a little bit of extra work that you're not going to get marked for, I posted some stuff to the extra resources. So, number 1, I found a video. I don't know if you guys know the YouTube channel Computer File, but man, is it good. They dig up all the old fossils and talk to them, like old fossils in the way that Han Solo dismissively refers to Obi-Wan Kenobi in the original Star Wars, that type of fossil. This is why C is useful and important by someone who was working in Bell Labs, and the guy who wrote the original C manual, the original book that, the original tutorial document on C programming. So that's cool. I recommend giving that a listen. It's 10 minutes. Again, none of this is compulsory. This is all just for your information. And then I threw up the 1xC3 labs. So 1xC3 is an interesting one because it's like the version of this course that the comp sci people do, except it's also combined with a Linux, much heavier Linux component, and basically the laboratory exercises are supposed to be 4 hours, and they go into a fair amount of depth on various Linux-type topics that may be of interest to you. Most particularly relevant to the thing we were talking about yesterday was Lab 6 on environment variables and libraries. So if you want to actually have an exercise that will show you, is this going to download? Did I just... Oh, nope, there it is. It's just taking its time. There we go. So, if you want some actual activities that you can go through to learn how to actually properly construct a dynamic library, most of this will assume you're working in Linux, however, there you go. You can have access to it. This is you get this for free because I'm a nice guy. Normally, people have to pay a lot of money to take this course, so... So yeah, but yeah, if you go through these, I only do the ones that seem useful or interesting to you, obviously. So a lot of this is going to require, you going into, GitHub and getting GitHub archives and stuff, but, yeah, it's useful and interesting. So yeah. So yeah, I put that up. If anybody is interested in it, it's for your benefit. Otherwise, we can continue on. Jar Jar Binks is the greatest written character in the whole universe, no competition. Yes, with the possible exception of Shaggy. Because we all know that Shaggy is the ultimate organism. So... Yeah, and I should mention just briefly, if you're also interested in, the lectures that are supposed to complement the 1xC3 material, that's actually also up on my YouTube channel publicly, so if you want, there you go. You can be a Linux expert too, you just have to put in a little extra effort. As far as I'm aware, there's no equivalent in your program for this kind of stuff. So, might be a good idea to just, take a copy of it for future reference as well. But yeah, at some point, and this is kind of terrible, but this is going to be true. At some point, you're going to be required to know how to use Linux without ever having really been trained on it. So, it might be cool to actually go through that stuff. But anyway, anywho, let's talk about code and stuff. So, last time we were talking about dynamic libraries and how libraries are organized and all kinds of fun stuff like that. Now, let's introduce the Callstack. So, have you ever wondered how your computer keeps track of all of those pesky function calls? Function calls are stored in your system's function call stack, which is often called just the call stack, or, reverently, the stack. The call stack has a fixed or static size. If too many items are added to the call stack, this can result in an error called stack overflow, which is what stackoverflow.com is referencing. So if you didn't know why Stack Overflow is called Stack Overflow, it's because it's in reference to at one point, common error of Stack Overflow. In order to understand the call stack, we need to know some rudimentary data structures. So, have you talked about stacks before? Or do you know what a stack is? Do y'all know what a stack is? So, someone in the chat says, this is true. My friend got a co-op in software this summer, and they made him make Linux Docker container and a bunch of complicated Linux stuff, and he had to learn it all on his own. Yeah. Yup. Yeah, so let me illuminate what your degree is good for, you guys, you mechatronics folks. Your degrees give you a basis in mechanical and electrical engineering, but by the time you reach your third year and your fourth year, a majority of the courses that you're going to be taking are going to be software. So, while hypothetically you would get a job as like a control systems engineer or something, it's also possible that a fair number of you are going to make your way into the software industry. And if you are sort of angling yourself towards the software industry, learning Linux is not going to be optional. Not going to be optional. And even if you're like, oh, I'll just use Windows the whole time, it's like, yeah, okay, but the skills that you learn in Linux are going to be the skills that you need in Windows as well. So, yeah. Yeah, I think I know. It works the same as the stack for card resolution in Magic the Gathering. Probably true. So all you Magic the Gathering players, you probably already know this. So, so the call stack then. So what is a stack? Stacks of stacks. A stack is a data structure that always returns the most recently added element. This is also known as a LIFO, or last in, first out buffer. There are two primary operations on stacks. Number one, push. So if you have a stack, you can push an element onto the stack. The element that was the most recently pushed element is considered the top of the stack. When you pop an element, that's removing something from the stack. And the stacks are always removed in the reverse of the order that they were added. So the most recently added thing to the stack is the first thing that gets removed from the stack. And stacks are a very basic data structure. It's not in terms of implementation, it's not. It's like a list with some fancy access rules, right? You could easily write a stack in Python using a list and a push and a pop method, and that would probably take you all of 5 minutes to implement in Python. If you're using pointers in C, however, it takes a little bit longer. But yes, so you push and you pop. The kitchen metaphor is a stack of plates. How do you use the stack of dishes in your cupboard, right? You have a stack of plates in your cupboard. When you take a plate, you take the top plate, you put your food on it, you make your pizza pockets on your plate, you eat your pizza pockets, then you wash your plate, or you get a robot to wash your plate for you, and then your plate goes back on the stack of dishes. So, really, depending on how long you go between washing dishes, you probably only use the top 4 or 5 plates out of your stack of plates if you live alone, right? So, yeah. So, question: what exactly are we stacking here? That's the next couple of slides, but it's important. So, this is not a difficult concept in and of itself. In many programs, undo and redo actions are stored in a stack. So when you perform actions in Word, your actions get stored in a stack, and as you perform undo operations, you're going through the stack by calling up the most recent. Like, every time you pop an element, it's like the next most recent thing that happened. Yeah. So, just to visualize, this is, I'm going to get to it. Bands. We are stacking bands. We are stacking function call frames. So we are stacking function calls. So, a stack in operation, in case you need a visualization. If we have a stack that contains 1 and we push 2 on it, we then have a stack that contains 2, 1. Push 3, push 4, push 5, push 6. You'll notice that we have, like, things end up in that order, and then when we start popping elements, we get 6 first, then 5, then 4, then 3, then 2. So what is the call stack? Well, you know what? I think I'm going to do a demo. It's demo time. So, let's say we had a mildly recursive function. So a recursive function is any function that calls itself. Recursive factorial is a good example. So, int factorial takes an integer n, return n times factorial of n minus 1 if n is equal to 0, return 1, else. Technically, the else is unnecessary, but, you know. There we go. Quick, easy, dirty factorial. So, and then if I call factorial of 6, let's say, visualize execution. Oh, I've got a type error. Or a syntax error. Get out of there. Thank you. What is pop? Pop removes the top element off of the stack. When you pull out your plate to microwave your pizza pockets, that is a pop operation. You are popping the plate off of the stack. Does FIFO pop from the bottom? Yes. So, first in, first out pops from the bottom. First in, last out pops from the top. Very good, very astute. You guys are going to have to know what a FIFO is when you start doing hardware. Infinite loop, you say? Oh, yes, that's because I need to double equals that. Okay. Visualize. All right. So this is how the call stack works. I love Python Tutor because see how it says stack and heap? It is actually going to physically map your memory for you in a way that is what I'm talking about and accurate to the way that your computer manages its memory. So, factorial is stored on the stack. The only thing I wish with Python Tutor is that they reversed the stack, because right now it's like we add to the bottom and we pop from the bottom, and like with my plate metaphor, it's like reversed in the direction. So like for the next like 5 or 10 minutes, just like turn your laptop upside down and that'll work, okay? Yes. So we create a new instance of the factorial function executing, right? Factorial with n is equal to 6. So in order to calculate that, we need to open up a new factorial, right? Factorial with n is equal to 5. So 4, 3, 2, 1, there we go. And 0. So what happens with 0 is that's the terminating condition, right? So we have all of these instances of the factorial function that have been opened up because this is a recursive function, right? And we're going to get into recursion, but it really demonstrates the stack really well, so yeah. Yeah, you don't... when Grish is talking about wishing they knew about this for the assignment, then probably the Python tutor thing is what they're talking about. But anyway, so each one of these instances of the factorial running, these are what we call them stack frames. So all of the local variables that are being used by a particular function are stored inside of the stack frame. So when we then have a return value for this factorial, right? Unfortunately, it doesn't show the return values, but we have a return value of 1. That gets passed up, right? Then, like, we keep hitting these factorial values, right? I could probably, if I make it a little bit more explicit, I might be able to. So, int recursive is equal to this guy. I'm just going to put it in a different thing so that we can see it a little better. In fact, I'll make it the return value. That'll be even better. There we go. All right. Australian plates. Exactly! It's Australian plates. If it were also the case that those plates couldn't leave their house. Ah! So, on we go, on we go, on we go. Same thing. So we can see that in each of these, the return value is uninitialized. Like, we are in the process of calculating the return variable. So it's like the result of return is pending the outcome of this expression being evaluated, right? But in order to evaluate that expression, we need to open up another stack frame. And we need to open up another stack frame, stack frame, stack frame. Right? So finally we get to the n equals 0 case. The return value is going to be 1. We can then calculate the return value of this one is 1. The return value of this one is 2. 6, 24, 120, 720. And then that's the final answer. This doesn't print anything or anything, but yeah. So that's how. So you'll notice that through this point, right? These when a function finishes execution, it is popped from the call stack. The reason that local variables are local is because they also get deleted when the stack frame gets deleted. That's the actual reason local variables exist. In case you didn't know that, which probably you didn't. Global variables are either stored in the main frame or in the heap frame. So main can have its own variables, obviously, and those are as far as C programs go, variables in the main function, well, they're still local to main, but it's kind of like there's sort of this thing where You can declare things global by putting them outside of main, basically. There's also a keyword for it, external. So what's the difference between stack and heap? Well, to be completely honest with you, I'm not an expert on it. I have not gotten as deeply into heap memory as stack memory, but I do know that arrays are stored in heap memory. So, like if you, I believe that's where things like when you do my dynamic memory allocation, I believe that's where that gets stored. So, like if you were to, and this is not something you need to know until we like a number of topics from now. But if you were to declare, for example, int star sum list is equal to malloc size of int times 20. Again, we're going to do all of this. This is like skipping ahead. I'm pretty sure that malloc will put it into heap memory. Incidentally, I highly, highly, highly recommend this CTutor website when you start working with pointers. Yeah, there it goes. So the way that it works is SumList has a pointer which points to an array that's stored in heap memory. So the array itself, the memory that constitutes the array itself, that's not stored in the stack frame. But the pointer that points to it is. So, like, this pointer is local, but the array itself is stored in a different memory style, or in a different part of the memory. Yeah, so there you go. That's what heap memory is used for. One of the things it's used for. Good. So, Callstack functionalities. The Callstack enables programs to step into functions while keeping their place in the program that called the function. Functions are properly thought of as sub-programs, right? So, think of your operating system in this manner, right? So your top of the call stack is like the factorial function and like 7 different calls to factorial. Then you've got main. Then you've got the shell, right, that's running main. Then you've got the operating system that's running the shell. Then you've got the kernel operations that are running the operating system. Like there's a lot going on in your call stack below the level of the C program that you're currently executing. Does that mean all arrays are global? The array is stored in global memory, but the pointer to it is not, and you can't access it without knowing where it is. So, yeah. So, the call stack supports the creation, maintenance, and destruction of each function's local variables. This is also known as the namespace. You'll sometimes hear me refer to this as being a namespace, although that's more of a C++ term. It's still a good term. The call stack keeps track of the return addresses that each function needs to return control to the invoking function. So all of the bookkeeping with respect to where you need to pass data to, what the return value is, where you are in the function, all of that stuff is stored inside of the call stack. Think of the previous stack example, but replace the numbers with all of the data necessary to execute a function, including variables. These are known as stack frames. Yeah. So, another cooking metaphor. Let's imagine we are baking a pie with recipe cards. And the recipe card for the pie references 3 other recipe cards in the same box. We'll call them complex ingredients. These complex ingredients are flaky pastry dough, lemon custard, and simple meringue. The algorithm for completing the task would be as follows. Proceed until a complex ingredient is called for. Take the corresponding recipe card and place it on top of the card which uses it. Follow the new recipe. If another recipe is required, go to step 2. If finished, go to step 4. Remove the complete recipe from the stack of recipes and put it back in the box. Resume the recipe underneath at the step that called for the complex ingredient. That is how functions work if functions were baking. An example. I already did an example. So I'm going to skip this one because I did a better example than this. I showed you a dynamic example. When does the array in the heap get destroyed? When you execute a free operation. So you actually have to manually deallocate it yourself. Because it's C. That's why. So, for example, free sum list. I think technically I should have to import standard lib for this. Include standard lib.h, I think. I don't know. It's some artifact of it's some artifact of ctutor that it automatically includes standard lib, I guess. I guess it needs standard lib to be able to produce its output, so it just includes it. Close. So you allocate the list, and then free deallocates it. And then it puts a poop emoji in the pointer. So the pointer no longer points to anything. So the pointer, it's like, the array has been deallocated, but the pointer still exists, so it points to crap. It's a crap pointer. That's funny. But yeah. Could I explain C using, all of C using food? I'll try. I can... Okay, this is what you can do. This will be our game. When you need something explained, you now have the option as a student of this class to say, explain this with food, please. And I will do my best. How do you initialize the stack? You don't have to because the operating system initializes it when it starts up. That's part of the startup routine of every operating system is to initialize the call stack. So, there you go. So let's talk about variables. We've been talking about variables quite a lot, so let's talk about variables. There are two main ways that programming languages will pass data into their functions. By reference, examples would be Perl, Visual Basic, and Fortran. In these languages, variables are passed into functions as references to data rather than the data itself. This means that modifying the function argument inside of the function will modify the variable passed into the function within the context of the calling program. So what that essentially means is that you've got you don't have the variable itself. You don't have the value. You have a reference to a memory cell. So that makes every input an implicit output of the function as well. But yeah. What is a pointer? Oh boy. We're going to talk about pointers in two topics, my friend. And yeah, don't worry, we're getting there. We're getting there. But, you know, to tie that back into here again, passing by reference means passing by pointer rather than passing by value. So, the short answer is that a pointer is a memory address being manipulated as if it were a value. But, and you're going to see the word pointer pop up more and more the deeper we get into C, because, like, the one essential skill of C programming that distinguishes it from most other programming languages is pointers. But we're going to get into it. So, passing by value. C, Java, and Python, with a little asterisk, they all pass by value. Python actually uses a scheme called pass by assignment, which is a little bit different. Basically, Python integrates the, any of the rules that apply to assignment into into passing when it takes arguments in a function. But like, for example, in Python, if you have an alias of a list, that gets passed as an alias, and like lists get passed as aliases into functions. So if you modify a list within a Python function, that change will register externally. Yeah, can we talk about pointers when we cover pointers, because otherwise you'll get real confuzzled? Yes, yeah. For now, you don't have to know the specifics of it. You just know they exist and that it's a major topic and that it's coming up. So yeah. So in C, when you pass by values, the bit values of the variables themselves are passed into functions rather than references to the memory that contains them. Modifying an argument does not affect anything outside the function's local context. So changing, like writing to the arguments of a function in C, does not have that effect. Does not pass outside of it. C can pass by reference as well using pointers, but you have to do the legwork yourself because this is C. So here are a few miscellaneous things. Type defs. This is like, and now for something completely different. The typedef keyword allows us to define type synonyms. Typedef unsigned char byte. So if we want to, within the context of our code, use the term byte as if it was a data type, and as so long as we want, basically we can relabel data types. This allows us to use the new byte type anywhere a type must be declared. So, for example, if I were to pull up this and I said something like typedef int I, capital I, let's say, then anywhere I use an int, I can replace it with a capital I, which in theory would save you a certain amount of typing. But you don't have to, right? You can use a mix. See, everything works. The program works as we expect it to. So it's just a relabeling of data types. Some of the data types can get, like, pretty long. So, like, for example, in C, you have long unsigned int, which, if you type it out, is just very long, so you can relabel it as something else. The compiler will swap in the type's synonym at compile time. Type synonyms can be very useful for improving the readability of your code, as they allow for more descriptive type information. By convention, data types are capitalized. So there you go. Enum with terror. Another way that we can define custom types in C is with enumeration. Can you say typedef int float? Ooh! Maybe. Let's see. Typedef int float. Let's see if that's an error. 2 or more data types in the declaration specifier. Yeah, okay, so it's a keyword, so it's not an identifier. That's... Yep. Nope, you're prohibited from doing typedef int float. Float is a keyword, and thus will be prevented from being used like that. Float is definitely a reserved word. For sure. So, another way that we can define custom types in C is with enumerations. So, this is an example of an enumeration. Enumerate Pokemon status: faint, sleep, paralyzed, poisoned, freezed, burned, or none. Not only is the type available, but the enumerats, these are called enumerats, may also be used as literals. So, Pokemon status is now a valid data type, And these guys are all valid literals. So you can just use them in expressions. So poison can be used as, like, to compare. You can. So in this example, we have a variable stat, which is of type Pokemon status. It starts out as none. If stat is equal to poison, hit points equals hit points minus hit points divided by 16. If HP is less than 0, status equals faint, etc., etc. So yeah, so that's an enumeration. They can be, these guys are almost more useful for code readability than simple type defs. So, in reality, each of the enumerats is an alias for a literal bit value. We can expose these with the following program. So if you have an enumeration and you print them as integers, you'll we can see what we get. Boop. Come on. There we go. So, I'm just going to do a simpler one to type. Enum Q, what is it? A, B, C. Yeah. Printf as a integer A, B, and C. Oh, I gotta delete that, don't I? And I gotta put the other one back in too. There we go. So, A is 0, B is 1, and C is 2. So basically what enumeration is doing, what enumerations do is they just label this, like underneath the label, A is 0, B is 1, C is 2, etc., etc. It's just a way of, you know, it's a way of making the code more readable. Incidentally, I think you could probably also use, like, greater than or less than on these guys as well. So, 2 questions. What is a type synonym? Think about what a synonym is. Think about what a type is. Put those 2 concepts together. What are literals? A literal is something like, you know, 7, or 5.3, or hello world, the string, or the character J, or in this case, these enumerats. Typically literals are they're elements of an expression that can't be broken down and are not variables or functions, typically. So, there you go. How does the computer distinguish between 0 and A in this case? If we were to ask the computer to compare both values, A equals 0, would it evaluate as true? Yes. Yes, that would be the case. So, print A is equal to 0. I think D, we're going to have to... So when you're interpreting booleans as integers, anything that's 0 means false, and anything that's not 0 means true. So that's true. 1 is true. So yeah. The thing about C programming is that you can definitely mix and match your types. You can compare ints to floats. You can compare enumerations to integers. That's particularly useful. Yeah, it's like really, like, it's just like a paper-thin disguise for a number. Are true and false literals in Python? I don't know. I don't remember if they're capitalized, but yes. And they aren't in C unless you include standard Boolean, the Boolean library. Scope. Don't be a dope. Consider the scope. The scope of an identifier denotes what parts of the program that identifier is accessible in. Levels of scope are often called contexts or namespaces. We are often taught that scopes can be local or global, depending on whether the identifier is available only within a particular function, that makes it local, or throughout the whole program, that makes it global. This is a grammar-based understanding of scope, since we tell the scope of something by looking at the program's structure. Note that public and private objects in object-oriented languages are related but distinct. So, relating scope to Callstack. A better way to think about scope is to think about how the Callstack works. The top-level frame in the Callstack is the local context for the program that's currently being executed. Functions are here considered programs. This is the most local context. So, when you execute the factorial function, this is the most local context. This is a context, this is a context, this is a context, this is a context. These are all scopes, right? Each one of these factorial calls, like, the scoping on these, like, each, like, what am I trying to say? Imagine a pyramid, right? Each layer of the pyramid is a scope. This guy's scope sits on top of all the rest of the scopes, and in certain languages you can even look up or look down through the previously declared scopes. But, you know, that's yeah. So, okay, a couple of questions. When I finish this slide, I'll answer the questions. The reason local variables are not accessible in a more global context is that they are deallocated before program control returns to the calling program. This is why local contexts can access less local contexts, but not vice versa. So, locals can access globals, but globals can't access locals. That's a long way of putting it. So, question. Is there a way to set what value those literals get when you initialize them? Maybe? Let me try something. Yeah, you do it with equals sign. I didn't know that. I just took a guess, and my guess was correct. Ha. Yeah, so if you use the equals sign, you can set what the integer is. You're kind of confused. Are enumerats integers? Yes, but then again, most things are. Like, even pointers, like, everything's a number. Everything's a number. These guys are numbers too. Oh, that's interesting. So when you set this guy, it keeps counting from whatever this guy is. That's interesting. Yeah. Very interesting. Yeah, so that's actually a good, like, that's the flavor of C programming, really, is like, oh, I wonder what this does in this context. Oh, it does something unexpected. I assume there's a reason for that dates back to the 1970s. But, you know, C is a great language for people who love, like, pedantic edge cases. Yeah. So, storage class modification. We can change the scope of identifiers in C using storage class modifiers. So we've got 4 keywords: auto, register, external, and static. So auto variables are the regular variable that you all know and love, right? They're stored in the call stack. They are initially filled with smelly garbage. They are scoped to within the function, and their life is ended when the function ends. Extern, this is your basic global variable declaration. External variables are stored in the data segment, that is to say heap memory. They have an initial value of 0. Their scope is global within multiple files. So you can have global variables that go across multiple files in C, which is kind of cool. And they exist until the end of the program. Static variables are interesting. They're like halfway between a global variable and an auto variable, or an auto and an external. So it's stored in the same place as the external variable, and it gets the same initial value of as the internal variable, but it's still local to the function. So what static variables allow you to do is to retain information between function calls, but not place something in like the global namespace. So it's still inaccessible to, like, if you had let's say you had function f with a static variable in it, static variable x. X is accessible within any call to f, but not accessible to main. And it's terminated at the end of the program. So register is kind of interesting. That allows you to store variables directly in the CPU registers. So the primary use of this is optimization, because CPU registers are the fastest memory. So the things that are modified most frequently, you want to store permanently in the CPU's registers. Otherwise, they behave exactly like auto variables. Storage classes continue. Okay. Auto explicitly declares a variable using the default scoping rules. As such, the auto keyword is rarely, if ever, used. It's really just included for legacy purposes. But yeah, you can declare your variables auto if you want. Extern declares a variable as having global scope, implicit when the variable declaration is outside of all functions in a C file. Static, visibility rules from auto. So you get the visibility rules from auto combined with the data persistence of extern. Visible only inside the block it's declared in, but the variable's value is persistent between different executions of the same function. And register follows local scoping rules, suggests that the compiler place the variable in register memory rather than RAM memory. Can you tell this is my second straight hour? The compiler has the right to say no, however, and will perform this sort of operation automatically if you ask nicely. That is to say, use optimization flags. So yeah. And that's it. That's okay. Next, we're on to recursion. So, yep. Any questions? Anybody got any questions? Any questions? Any questions? So if you declare a variable outside of a function, it is global by default. But if you want to declare a global variable while in a function, you have to say something like extern int count. Yes, precisely. How do we test our code in main for C? I'm having a hard time figuring out Like, can we just put printfs? Yeah, that's how you test. The other way that you can do that is with ctutor. With ctutor, you can just kind of peer inside the various variables at any point. Yeah, so either use print statements to view your output, or use the tutor program, ctutor. What happens if you delete system32? I don't have that problem because I run Linux. I don't have a system32. Ha! If I go folder by folder and start deleting stuff, how will that break stuff? Bit by bit. Yeah. The equivalent in Linux of the equivalent in Linux. I'm not going to. I'll write it in a safe way, but the equivalent in Linux of deleting system32 is cd/rm sudo rm r star. That deletes everything on your disk. This navigates to your root directory. This deletes everything. With administrator privileges. But you have to enter the password. But yeah. Yeah, if you delete system32, that opens up an option to download more RAM. If there's anybody listening to this, don't delete system32. Just don't do it. I meant byte by byte. Yes, thank you. Thank you for that most obvious of puns. You approve. I approve, and you will get an A in my class. Okay. Okay. Well, I'm gonna log off here. Take her easy, folks, and I will see you on Thursday, the day of Thor. Take her easy.